Electrostatics, Coulomb's law. We're going to start off with some review of Science 9. Hopefully you've learned that all matter is made up of atoms. And one of our models for an atom is the Bohr model, where we have a nucleus that is positively charged, and then we have electrons that are orbiting, although we don't even like to use the word orbit anymore. We like to use the word electrons in energy shells. We prefer that, because orbit makes it sound like they're going around and around. They really aren't. They're far weirder than that. Then when atoms bond together to form solids, these electrons can be tightly bound to the atoms, like glass. We call those insulators. They don't pass electrons through them very easily, very willingly. Or they can be free to move around, as in metals. These will be conductors. So you can have nuclei with tightly bound atoms, or you can have nearly free atoms, and the electrons are free to go from atom to atom to atom to nucleus to nucleus to nucleus to nucleus, and they're free to move around. Insulators and conductors. You learn this in Science 9. You probably don't learn this explanation, but you learn that insulators don't conduct electricity, and conductors do conduct electricity. It's where the word conduct comes from. You also learn in Science 9 that all subatomic particles, like protons, electrons, and neutrons, have a property. We call this property charge. And it's charge, this property, that's responsible for electricity and magnetism. Some basic facts about charge. So there are two types of charge. What do we call the two types of charge? Positive and negative. Hello. There we go. What do we measure charge in? What are the units for charge? Nope. Volts is not a measure of charge. Volts is a measure of sort of energy, but not quite. I'll give you a hint. It's in the title. It's in the title. Coulombs. Charge is measured in coulombs, symbol capital C. And then we're going to give you a new variable today. So mass is represented by which letter in our equations? M. Force is represented by which letter in our equations? F. Charge is not represented by the letter C. C is actually taken by something far more important, the speed of light. Charge is represented by the letter Q, lowercase or uppercase. Usually I'll use a lowercase q for a tiny charge and an uppercase q for a big charge. The same way as in gravity, I used a lowercase m for the satellite and a big M for the planet. We'll carry on, that's a handy convention. Why Q? Oh, patience. Another important fact about charge is that it is quantized. This is where the word quantum physics comes from. And this is why we use the letter Q. Now, what does quantized mean? Quantized means that charge comes in a smallest chunk, like money. What's the smallest unit of money? The penny. I know we phased the penny out, but we still calculate with it. When we give you dollars, we always round to the nearest cent. A penny is our quanta of money. So with money, there is a smallest unit, the cent, and any amount of money can be broken down into a certain whole number of pennies, n pennies. But you can never have a fraction of a penny. You may have that happen on your calculator, but in real life, it's not allowed to exist. We've got to round to the nearest penny. Money is quantized. In fact, the smallest unit of money is the cent. Any other amount is the number of pennies times 1 cent. With respect to charge, the smallest unit of charge is called the elementary or fundamental charge. This word is going to be important. I notice my screen is moving. Okay. For some reason, my screen is moving around like that. I'll have to fix that. It's called the elementary or fundamental charge. And it turns out this is the amount of charge on an electron or proton. Protons and electrons define the elementary charge. They have the same charge, it's just one's positive and one's negative. What is the elementary charge? It's on your formula sheet. It's on your formula sheet just below where it has the mass of the planets and the radius of the planets. Somewhere in that section of information, you'll see the elementary charge. What is the elementary charge? 1.6 times 10 to the negative 19 coulombs. That's the charge on a proton. Negative 1.6 times 10 to the negative 19 coulombs is the charge on an electron. This is the elementary charge of the universe. Sorry, it's an inconvenient number. Well, it is what it is. Do you have to memorize it? No, it's on your formula sheet. You probably will memorize it in this unit because you'll get sick of looking it up. The same way as last unit, most of you memorized that big G was 6.67 times 10 to the negative 11, but by the end of the year you'll have forgotten it. You can look it up. Okay. All larger charges are multiples of E. You want to know how much charge you have? Count up the number of electrons and multiply that by 1.6 times 10 to the negative 19. If it's negative charge. If it's positive charge, count up the number of protons and multiply that by 1.6 times 10 to the negative 19. Nerd comment. You may be aware that actually we have since learned that there are smaller particles called quarks that make up neutrons and protons, and they have charges of 2/3 or 1/3 of the elementary charge. So it turns out this is actually not the smallest charge, but we're going to pretend that it is. We're not doing quantum physics here. In this course, you're going to get a data page, you've seen it already, that lists the masses of the subatomic particles and the fundamental charge. You need to make sure you know where those are because you're going to be needing the mass of a proton, the mass of an electron, and the charge on a proton or an electron. The data page does not explicitly list the charges of the particles, so you'll need to remember the following. The symbol for an electron is E negative. The charge on an electron is negative 1.6 times 10 to the negative 19 coulombs. Negative elementary charges. Negative 1 elementary charge. The symbol for a proton is P plus. Its charge is positive 1.6 times 10 to the negative 19 coulombs. The symbol for a neutron is N0. What's the charge on a neutron? Zero coulombs. Okay. So, our first example. I wrote, although this does not need to be memorized, you might recall from Science 10 when you look at radioactivity that an alpha particle, which you symbolize with an alpha, is a helium nucleus containing 2 protons, 2 neutrons, and no electrons. What's the charge on this particle? Well, it's got 2 protons, which is going to be 2 times 1.6 times 10 to the negative 19 coulombs. It also has 2 neutrons. What are the charge on 2 neutrons? 0. Has no electrons. What's the charge, this is meant to be really obvious, on no electrons also? So, you know what? The charge on an alpha particle is 3.2 times 10 to the negative 19 coulombs, and it's positive. I'll put a positive there. You don't need to. I just did in our notes to remind you, be careful with your signs. Make sure you know whether you're dealing with protons positive or electrons negative. Hopefully nothing really new there. Science 9 and a little Science 10. Now let's get into a little more detail. For a conductor, electrons flow easily. For an insulator, Electrons cannot flow, but we can shift the shells or the orbits slightly, and we call this polarization. You can polarize an object so that it will have a net charge even though its overall charge is 0. You can charge certain sections of it. This is one of the 4 fundamental forces. Charges exert a force on each other. Fill in the blanks and then draw the direction of electric forces. What do you learn in Science 9? Like charges. Unlike charges. Vikas, that's going to be your cue for this whole unit. Like charges. Unlike charges. There is so much information in that sentence, you can almost derive the entire universe with a bit of cleverness from that right there. The fact that like charges and unlike charges. So here is a picture of 2 like charges. What will they do to each other? So there'll be a force this way and a force that way. Here are 2 unlike charges. What will they do to each other? Okay. For example, so we can explain a lot using what are called charge diagrams. Now understand, Raj, in real life, there's trillions of charges that are moving back and forth, but for the purposes of our diagram, we'll draw like 2 or 3, and just as long as we see what there's more of, more positives or more negatives. So a negative rod, let me zoom in, is brought close to an insulating ball. Now the ball initially is neutral, so I'm going to say that it's got 2 pluses and 2 minuses. Really, it has 50 trillion pluses and 50 trillion minuses, but it's neutral. Okay? Did you see initially the ball was attracted? Now, why? Well, because this ball is an insulator, we can polarize it. For a split second, what was happening was negative, 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 negative. The negatives in the ball were moving to the right, leaving a net positive charge closer to the rod. And because the positive was closer, it has a stronger attractive force, and that's why the ball touched the rod. You okay with that, Kiowa? But as soon as that happens, then a couple of these negatives are going to jump across. So you still have negative, 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 negative. You still have positive, positive, and 2 negatives from the original, but you've got a bunch of extra negatives now that have jumped across because the rod is so negative, it wants to get rid of its negative, because like charge is what, Vikas? Now, as soon as they jump across, this is no longer, the ball is no longer neutral. What's the net charge on the ball? Also negative. This is negative, a tiny bit less than it was before, but it had trillions to spare. This is negative, so these are like charges. What will like charges do? Repel. And so that's why you see it jump first of all, because it's polarized, and then as soon as it touches, some of the electrons jump across onto the ball. Now it's negatively charged, and you have negative, 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 and you have an overall negative charge there. I'm not even going to write the positives, even though they're there. So we can explain that. By the way, Benjamin Franklin is the person who decided that electrons were negative and protons were positive, and he named them wrong. Really, if we could change one thing in engineering, in electrical engineering, we would tell Ben Franklin, look, call the electrons positive, because they're the ones that are moving. He didn't know that those were the ones that were on the outside of the orbital shells, and that those are the ones that are moving, but it sure would be nice to do math with positives moving around instead of negatives moving around. That's why in Science 9 you have the whole, when things are ionized, when ions form, well, it's losing an electron. Losing makes it positive. Shouldn't losing make it negative? Well, no, it's because it's losing a negative, and it's a minus minus, which is a, well, he named them backwards. Should have changed it. So this is called charging by conduction. Conduction is when you touch two objects together. In Science 9, I teach my students that conduction requires contact. You can also charge by induction. Induction is indirect. You can create charge without actually transferring charge from one object to another. Let me show you how. Suppose you have, we're going to do a charge diagram, two uncharged or neutral metal spheres, and they're fixed onto supports and they're touching right now. Then I'm going to bring in a charged negative rod. I'm not going to touch the metal spheres though. So here's my negative rod. Clay, what's the charge on the rod? Negative or positive? Vikas, what will like charges do? So here's what's going to happen. All the negatives are going to move to the right-hand sphere, and that's going to leave the left-hand sphere with a net positive charge. You okay with that? Now, have we touched, with this rod, have we actually touched this yet? So have we transferred any charge? Have we conducted any charge? No. Now what we're going to do is we're going to grab the base of the second sphere carefully and just slide it to the right. That's going to leave us with this. Have we touched the rod to the spheres yet? No. But then if I remove the rod, although I initially started with two neutral spheres, look, I was able to charge both of them without touching. This is called charging by induction. Yeah. Yeah. In fact, if you want a good example, now this is a very, very simple example of charging by induction. How many of you have an electric toothbrush? Okay. There's no metal contacts on the bottom of that electric toothbrush when you put it into the case because you don't want conduction around water. It's an induction charger in there that's recharging the battery in the electric toothbrush. Probably the next generation, or maybe two generations of phones from now, they'll all have induction chargers. Some of the Android devices do, and I think the next version of the Apple phone is rumored to have an induction charger. All that means is, if those of you have an Android device, how many of you have one that you can just lay down on a mat and it will charge without having to plug it in? It's charging via induction. In a much more complicated system than this, but a bit of cleverness and we can come up with it. We're good engineers. Okay. All of that is preamble. What you need to know from all of that is what the elementary charge is, 1.6 times 10 to the negative 19. What the units are for charge. What are the units for charge? What are the units for charge? Coulombs. The types of charge. Okay, and you need to know the electrons are negative and protons are positive, and 1.6 times 10 to the negative 19. The last thing you need to know is that like charges, unlike charges. You do not need to know induction and conduction. That's just kind of nerd trivia. Here's what you're going to need to know. It turns out, you've seen that I can apply a force between charged objects. That force can be calculated. Coulomb found that force equation, and his equation looked like this. F, and I usually put a little E for electric force, Fe equals KQ1 Q2 over R squared. This is the force of attraction or repulsion. We'll figure out the direction. How? Like charges, unlike charges, repel. We'll figure out the direction ourselves, but the magnitude is given by KQ1 Q2 over R squared, where Q1 is the charge of the first object in coulombs. Q2 is the charge on the second object in coulombs. D or R is the distance between the charges squared. By the way, what equation does this look an awful lot alike? What equation does it look an awful lot like? Clay. Gravity. Gravity. Yeah. In fact, a lot of what I taught you in the last unit, you're going to see translates over into this unit. We're going to have electric fields. We're going to have, the potential energy equation is going to look really, really simple. It's going to be relative to 0 at infinity. It's going to look very similar to what we have here. This number right here, K, is like big G. It's the number that Coulomb found that he had to put there so that Coulombs times Coulombs divided by square meters gives you newtons. Big G for gravity was 6.67 times 10 to the negative 11. Thankfully, K is a much nicer number. It's 9 times 10 to the 9th. It is on your formula sheet. Somewhere on your formula sheet, probably just below the elementary charge, is K. What do they call it on your formula sheet? Oh, constant in Coulomb's law. There you go. Okay. By the way, what was big G? 6.67 times 10 to the what? Negative 11. What's K? 9 times 10 to the positive 9. Electricity is a way stronger force than gravity. How much stronger? 10 to the 20th stronger? The difference between positive 9 and negative 11. Gravity is a very weak force. We think it's big because we live on a big planet. But really, it's the weakest of the four fundamental forces by a long shot. By a long shot. Okay. Force is a vector, but I'm not going to put any vectors on the right-hand side. Instead, to find the direction of the force, we're going to use, because here's your clue, like charges, unlike charges. So we'll add the direction ourselves by looking at the polarity of the charges. Example 2. Example 2 says, find the direction of the electric force on the, on the positive Coulomb charge, on this guy, right there. Don't circle yours. I'm just going to highlight it so you can see we're talking about this one. I will not be giving you an equation that deals with 4 charges. I will not be giving you an equation that deals with 3 charges, the same way as I never gave you an equation that dealt with 4 planets or 3 planets. We can deal with 2 at a time. So, you ready? Ignore those 2. Only look at this charge. Looking at this charge, is it repelling Q or is it attracting Q? Attracting. So is it pulling Q down or pushing Q up? Down. So there would be a force. Yes? Now only look at this charge here, this top right one. Is it repelling Q or is it attracting Q? So is it pulling Q to the right or pushing Q to the left? Ignore these 2, only look at this one. Is it pulling Q towards it or repelling Q away from it? Repelling up and away? Which charge is bigger out of these 3? It's a trick question. Say it, you're right. Which charge is further away from this? Got to be because it's the diagonal, the hypotenuse, right? And because there's a distance in the bottom, I think that means that this is the weakest force. So I agree it's going to be like that, but it's not going to be very big. If I wanted to find one force, I would take all 3 of those vectors and I'd add them together. Any thoughts on how? Yeah, it would go like this, to the right, down, and then up a little ways. I think the net force is still going to be pulling him, at least at this point, towards that bottom left corner, at least right now. Now, as soon as it moves, of course, now your forces change. This is actually a very difficult question to handle without calculus. But we can get the direction right now. Right now, at that moment, it would be getting tugged that way. But the closer it gets to here, the bigger this repulsion will get. There's probably a break-even point where everything cancels somewhere right around here, where all the forces cancel out. So to solve force problems, we're going to express the charge in coulombs, if they didn't already. Use Coulomb's law, and then to get the direction, we'll use like charges repel, unlike charges attract. Technical comment here, Alex. If we have unlike charges, one positive, one negative, so if I put a positive number and a negative number in there, what's a positive times a negative? I don't want a negative answer. I don't want a negative answer. And so we're not going to put the signs in here. We're going to decide the direction by using like, unlike. And so you may see, you guys have seen absolute value in math. Some textbooks will actually put an absolute value sign around the charges, just to remind you, don't bother putting signs in. I'm not going to put an absolute value sign. What I'm going to tell you is for forces, forget the signs. Don't worry, we'll get the direction. So let's actually crunch one. It says, find the force on the electron in a helium ion. Okay. The electric force is going to be K Q1 Q2 over R squared. This is Coulomb's law. The electric force, what's K? It's our constant that we're going to use this unit. It's 9 times 10 to the 9th on your formula sheet. Charge 1, let's let that be the nucleus. What's inside the nucleus? 2 neutrons. What's the charge on 2 neutrons? Oh, 0. 2 protons, so that's going to be 2 times 1.6 times 10 to the negative 19. 2 elementary charges. There's the first location. Is that okay, Kiowa? Then it wants us to find the force on the electron. So here we're going to put the charge of the electron. It's negative. I'm not going to worry about the negative. I'm going to ignore that. Instead, I'm just going to put the charge of one electron. What's the charge of one electron? It's the elementary charge. No, I'm not going to put a negative in. I just said that. 1.6 times 10 to the negative 19. All divided by the radius. Oh, it told me in the question. It says 2 times 10 to the negative 11th, and then it's over R squared. Let's crunch this on our calculator. Yeah, I couldn't get the old one to work again. Nope. I'm typing in these numbers here.
Yeah, I'm just.
I know. I'm gonna give me a bit of time. I'm gonna see if I can buy one or find one or revive one. I lost my hard drive, and some of the obscure stuff, including my old virtual TI, haven't translated over. I'm gonna work on it though.
I got one I can send over. It's like the old one you had.
Pardon me?
I got one I can send you over.
We'll tackle it later. Did you get 1.152 times 10 to negative 6? Someone else? Yep. I'll go 1.15 times 10 to negative 6. Units, it's a force. Newtons. Now, that force may seem really small. It's massive. Well, no, Mr. Durick, it's 10 to the negative 6. That's not very big. Yeah, but what's that force on an electron? How much mass does an electron have? Not much. Do you know what the acceleration is? Hey, let's calculate it. I said here, although the force you calculated in example 3 may seem very small, we should note we're dealing with electrons, which have very small mass. If we were to find the acceleration of the electron in example 3, the acceleration when I divided by the mass of an electron, which is 9.11 times 10 to the negative 31, is 1.26 times 10 to the 24th meters per second squared. It's huge. In atomic terms, electric force is massive. I like example 4. I like example 4. Example 4 is a nice question. says, find, now I need to introduce some new units to you. Okay? 1 Coulomb, don't write this down, 1 Coulomb of charge is massive. In fact, if you touched something and absorbed 1 Coulomb of charge, not only would it kill you, almost certainly you would burst into flame and your skin would char. It's massive. Okay? So what we're going to use most of the time is micro coulombs. So you're going to see in front of the letter C that thing there, the mu. And all you need to realize is whenever you see that mu, you can just replace it on your calculator with a 10 to the negative 6. Well, with a times 10 to the negative 6. So there's the first thing. Okay? So this is negative 2 microcoulombs. This is 1 microcoulomb. This is negative 1 microcoulombs. Negative 1 times 10 to the negative 6. Positive 1 times 10 to the negative 6. Negative 2 times 10 to the negative 6. What does this question want me to find, Spence?
The electric force and direction.
On what?
On the one.
Okay. I want to find the force on that guy. Don't circle yours. How many charges are there grand total in this question, Spencer?
3.
The equation I gave you doesn't have 3. The equation I gave you only has 2 Q's, a Q1 and a Q2. How do we do this? We use something that we call the principle of superposition. That's a fancy word for saying we're going to do it in 2 steps. First step, I'm going to ignore that. Don't you cross it out, but I will. What I am going to do, this is what I would recommend. How about you call this charge 1, Q1, Q2, and Q3. What charge do I want to find the net force on, Spencer?
Q2.
Q2. So here's what I'm going to do. I'm going to find the force from Q1 on Q2. Magnitude and direction. That's going to be K, Q1, Q2, all over R12 squared. Is that okay? It's going to be 9 times 10 to the 9th. Charge 1. Am I going to put the negative in, Vikas? No. I'll decide the direction. Well, it's going to be a tract. I'll put the charge in 1 microcoulomb, 10 to the negative 6. Replace the micro with a 10 to the negative 6. Charge 2, positive 1 microcoulomb, divided by, what's the radius between charge 1 and charge 2? Careful. .2, because it's centimeters, right? Squared. Nine times 10 to the 9th, 1 times 10 to the negative 6, 1 times 10 to the negative 6 divided by 0.2 squared. And I get 0.225. Someone else want to double check me? Yep. 0.225 what? Units. Units. Newtons. Direction. Now look at charge 2. Which way is it feeling a force from charge 1? To the left or to the right? Look at charge 2. Look at this guy. Which way is it feeling a force from charge 1? To the left or to the right? Are they like or unlike? Attract or repel? So this is going to get pulled that way. To the right. You okay with how we figured that out? Unlike charges attract. That okay, Nick? Then we're going to find the force from charge 3 on charge 2. And this is usually how I write it, Q3 comma Q2. I'll figure out what I'm in. Which is going to be K, yeah? To the left. Sorry, to the left. Thank you, Manny. Sorry, to the left. Attract to the left. Good gosh, Mr. Dewick. Thank you. Then we're going to find the force between charge 3 and charge 2. Because I want to find the net force on charge 2. And this is going to be the radius between 3 and 1 all squared. And Q3, Q2. You okay with that? It's going to be 9 times 10 to the 9th. Charge 3 is 2 microcoulombs. Isn't it negative? I don't care about the sign. I'll decide the direction. Charge 2 is 1 microcoulomb. And I think the radius between charge 3 and charge 1 is 0.1 all squared. If I go to my calculator, I'll get 9 times 10 to the 9th times 2 times 10 to the negative 6 times 2 times 10 to the negative 6 divided by 0.1 all squared. And I get, you get 3.6, is that right? No, I'm wrong. I typed this wrong. I've got a 2 there. I shouldn't. Do you get 1.8? Direction, again, which way is charge 2 feeling a force because of charge 3? To the left or to the right? Because they're unlike, so attract. Dustin, you okay with that? Hey, how would I add 1.8 to the right plus 2.25 to the left? Minus, yeah. I'll subtract them. What will my net direction be? Who's winning? Right. Okay? So, final answer. The net force is going to be 1.8 take away 0.225. Dope. 1.8 take away 0.225. Do you get 1.58? Direction. Right. This idea of the principle of superposition, that's the fancy way of doing things. This idea of do the charges 2 at a time and then add them up vectorially is going to be important. Yes? But that's not what this question asked. This question only asked, what's the net force on the 1 Coulomb, on this guy in the middle? Doesn't matter, they're not acting on this middle one. All I asked was, what's the net force here? And then just imagine that somehow these are all thumbtacked in place and can't move. Okay? In fact, I always tell people, imagine little invisible angels are holding them in place and not letting them move at all. There will be some situations where we'll let one of the charges move and we'll let it fall. The only difference between this and gravity is, unlike gravity, stuff can also fall up because it can be repelled. Couple more, we're done.
Do you think? You know the clock's off?
No, but I'll fix that later. Oh, is the daylight savings? Okay. Example 4. At which point, approximately, could we put a positive 1 Coulomb charge so that it would experience no net force? Select one of A, B, C, D, or E. Okay. You know what? I think what I'm going to do is just try each location. So in location A, Suppose I put a little positive charge right there, 1 microcoulomb. Which way will this charge apply a force to it? To the left or to the right? This is positive, this is negative. So which way will this feel a force because of that guy? This is positive, this is negative. They're unlike charges. What can you tell me about unlike charges? They attract. So this would feel a force that way from the first charge. What if I covered this guy up? What direction will this charge feel a force from this guy? This is positive, this is negative. Which way will this charge feel a force? To the? This is positive, this is negative. What can you tell me about unlike charges? They attract. So it will also feel a force to the right. Can you ever add to the right plus to the right and get 0? That's meant to be really obvious. Don't overthink it. Can you add to the right plus to the right and get 0? No. This can't possibly be the right answer. Hey, let's try over here. I'll try the 2 outside, then I'll try the 2 inside. Okay? What if I put the positive charge right there? Which way will it feel a force because of this guy? To the left or to the right? Attract. Again, cover this one up in your head now. Which way will it feel a force because of that guy? Can left plus left ever equal 0? Can't be that guy. It's in the middle? Why can't it be right here? Well, we would have that way plus that way. How would I add those 2 together? So if I add that plus that, do I end up back where I started from? Do I get 0 as an answer? So it can't be that one. I agree, it's one of the 2 in the middle, B or D. Which one? Max? Let's see. If I put a positive there, which way will it feel a force because of this left-hand charge? To the left? Which way will it feel a force because of this right-hand charge? But isn't that also going to be true right here?
Yes.
But what?
The second one is stronger.
Bigger charge, so it can be further away. Good. It says explain your answer. We just did this whole process that I just did. I wouldn't write a whole paragraph. I'm not going to ask you a question like this, but hopefully you followed my explanation. We just derived the answer ourselves. It's got to be location B. That's the only place where you could have a net force of 0. Last one. It says find the electrical force, magnitude, and direction on the electron shown below. How many charges are there in this picture? 3. You know what? I don't have an equation for 3. Once again, we're going to use the principle of superposition. We're going to do 2 charges at a time. I'll call this charge 1, charge 2, and charge 3. You okay with that, Dustin? We're going to find the force of charge 2. You know what? I don't need to put the Q in there. Let's just go like this. The force of charge 2 on charge 1, magnitude and direction. We're going to find the force of charge 3 on charge 1, magnitude and direction. And then we'll add them. Now I have a feeling this time they're going to be at angles to each other. So you know how I'm going to add them? I think tip to tail. Force is K, Q2, Q1, over r squared. What's k? It's our constant this unit. 9 times 10 to the 9th, a little nicer than big G. Charge 2 is 1 microcoulomb. Charge 1 is an electron. What's the charge on an electron? Clay?
Negative 1.6 times.
Yep.
Negative.
Times 10 to negative 19.
19.
Am I going to put the negative in the equation, though? No, I'll use that to figure out whether it repels or attracts. But an electron has the elementary charge, 1.6 times 10 to the negative 19. How far apart are charge 1 and charge 2? 2 micrometers. 2 times 10 to the negative 6 squared. Micro is 10 to the negative 6. Come on. 9 times 10 to the 9th times 1 times 10 to the negative 6 times 1.6 times 10 to the negative 19 divided by 2 times 10 to the negative 6 squared. I caught that. And I get a force between those two vertical charges of 3.6 times 10 to the negative 4. Units, newtons. Direction. Is the electron getting pulled down or pushed up? What about the force between charge 3 and the electron? That's going to be kq3 q1 over r squared. Hey, is the distance r the same as in the first one? Is the distance the same? Is the electron this? What's the only difference? What's going to be the only difference in this equation versus this equation? I think the answer is just going to be twice as big, right? 7.2 times 10 to the negative 4. That's twice as big as 3.6. Direction. To the right or to the left? To the right or to the left?
Left.
Why left?
Because it's both alike, so they
Like repel. Well, an electron is negative, and charge 3, it tells me, is negative. So, left. This question says, find the overall force. Oh, how could I add those two together? So it's going to look like this. 3.6 times 10 to the negative 4 down. 7.42 times 10 to the negative 4 that way. And I drew my 7.2 roughly twice as long as the 3.6, just so I'm kind of the scale. Where's the resultant? From the tail of the first to the tip of the second, there's the force. Clay, say that again?
We're going to do trig now?
Yep. Now, I will say this, though. On your test, it'll be a right angle. It's not going to be a sine law, cosine law. This is Pythagoras and SOHCAHTOA, which I'm hoping is almost as fast as you can write and type. Right? I think it's going to be FE squared equals 7.2 times 10 to the negative 4 squared plus 3.6 times 10 to the negative 4 squared. the net force is going to be that number squared plus 7.2 times 10 to the negative 6 squared. Square root of that. I get 3.6 times 10 to the negative 4. Is that right, Mr. Duke? I typed it in wrong. 3.6 times 10 to the negative 4 plus 7.2, squared, Mr. Duke, plus 7.2 times 10 to the negative 4. I typed a negative 6 last time. Squared. Square root of that. That looks better. Do you get 8.05 times 10 to the negative 4? That's the magnitude. This said magnitude and direction. Where does my vector start? Top right. So I'm going to find that angle there. Which trig function? Which trig function? Opposite, adjacent. I can use tan. Yeah, I'd use tan because that's what they gave me. What of what? North of south, east of west, what of what? West of south. Yep. West of south. Let's get the angle. It's going to be the inverse tan of 7.2 times 10 to the 4th times 10 to the negative 4th, sorry, all over 3.6 times 10 to the negative 4. Dustin, if you want a little shortcut, you could actually just go inverse tan of 2 over 1, because that's what 7.2 times 10 to the negative 4 divided by 3.6 times 10 to the negative 4 reduces to. The 10 to the negative 4s cancel, and you have 7.2 over 3.6, which is just 2. Anyway, do you get, you know what? This thing's going to be in radians, isn't it? New calculator. Let's try that again. Yeah, 63.4 degrees. Like charges repel, unlike charges attract. That's how we get our direction. We can calculate forces using Coulomb's law. F equals K, Q1, Q2 over R squared. And if there's more than 2 charges, we go 2 at a time and we add them vectorially. What's your homework? Number 1. Number 2. Number 5. Number 7. Number 8. Number 14. By the way, if you look at number 14, ready? Here's a hint. Look at number 14. What path is the electron tracing out? A circle. So that means instead of gravity is what's pulling me in a circle, I think electric force is what's pulling me in a circle, and that, my friends, is how you can find the orbital speed. It's just a different type of orbit. Ooh, you mean all that stuff from the last unit is fair game? It's really going to overlap a lot with this unit too.